Chapter 6, Section 1, the second part here is simplifying rational expressions. We're going to go back to really kind of looking at how when we simplify fractions, it's easy to forget what's really going on when we do this. And so this is a nice review about how we're using factors that will end up being ones or the same numerator and same denominator, which allows us to basically prove that, like in this case, 15/40 is equal to 3/8. And what they do is you factor 15 to 3 times 5 and 40 to 8 times 5. And you could, and I usually what I teach students to do is always prime factor, and you'll not miss any common factors or ability to create fractions equal to 1. So you go, in this case, you knew that a common factor that was the greatest common factor in this case, which is 5, we can write that as a multiplication of fractions. Well, the rules of multiplying fractions is numerator times numerator and denominator times denominator when you multiply fractions. Well, we can break that out the other way and say that 3 times 5 over 8 times 5 is the same as 3/8 times 5 over 5. Well, 5 over 5 is equal to 1. That's why you broke that factor out that way. And basically using the identity property again, which seems kind of funny when we're dealing with numbers, but it gets pretty important that we have properties, which means that it says that this always works. If I have x and I multiply that times 1, where x can be anything, I get that x back. Okay, there's a property that says that. So to simplify these steps using algebraic expressions, where we're going to use variables, it says, if we have AB, which means A times B over CB, C times B, we could write that as a multiplication of two fractions of A over C times B over B. And also with that, we know that B over B is equal to 1, that identity of multiplication. So we can rewrite that fraction in a simplified way, saying that's just A over C. So what we're going to do with these rational expressions, like this one in example 2, is we want to find common factors. And a good way to do this again is to prime factor. I might even write this as 8 as 2 cubed, which is 2 times 2 times 2, x squared. And then I'm not going to miss any common factors. And 24 is 3 times 2 cubed times x. Well, they just left it as 8, right? Well, here's a factorization that they use, 8 times x, and 24 is 3 times 8 times x. Well, I can take these common factors and make a fraction out of those that are equal to 1. And that leaves x over 3 times 1, and I get x over 3. So factoring, basically looking at these expressions as factors or parts of a multiplication, is going to have a lot of value when we're trying to simplify rational expressions. And this is really just like a proof. I've just proven that this is the same or equal to this because all I've done is shown, hey, this is really just x over 3 times 1. It's kind of a special one, which is 8x over 8x, which will give you that expression. So we say that this simplifies, and when we talk about simplest form, just reviewing on fractions, when they say, express all your fractions in simplest form, we're going to have basically the same idea with rational expressions. And it means that the greatest common factor between the numerator up here, like x, and the denominator, in this case 3, the greatest common factor between those two is 1. What are the factors of x? 1 and x. What are the factors of 3? Or 1 and 3. Well, they have a common factor of 1, and that is the greatest one that there is. That means it's in simplest form. Well, let's look at example 3. And the strategy that we're going to go through is to factor. We've done a lot of stuff working with factoring polynomials. And we'll start out with the same strategies. So I'm going to look at this numerator here, 5a plus 15. Well, when I start factoring any polynomial, I want to look for common factors first. And in this case, 5 is the GCF between these two here, right? We're going to use that GCF for greatest common factor. You're going to hear factoring a lot. But the greatest common factor between 5a and 15 is 5. Because this is really 5 times a, and 15 I can write as 3 times 5, right? So they have a common factor. I can use the distributive property and rewrite that as 5 times the quantity a plus 3. Now that doesn't do in itself anything to simplify, but what I want to do is then factor my denominator and see if I have any common factors, and I have 5 that is common. And in this case, I've prime factored this. These 5 is prime and a plus 3 is prime. It only has 1 in itself as factors. And 5 is prime and 2 is prime. And if you go down to primes when you factor, which is not very difficult, especially with numbers, sometimes we'll do the hard stuff, do the hard factoring when we get into bigger polynomials, and forget about common factors. But I think if you prime factor all the time, make sure you'll not miss any things or any ones I can create as fractions to simplify this original. Okay, so this simplified is a plus 3 all over 2, and then they go back and they take the original, and the results are the same. So since we don't really have an equation, we just started with an expression. How can I check this again? And this is a strategy of checking where let's just take a number like 2, though we want to be careful. In this case I don't have to worry about it, but I don't want to use a restricted value. We went through before about making sure that you don't ever create a denominator of 0 or a division using a divisor of 0. So you got to be careful. But in this case we have a constant in the bottom here, a 10. So they say let's try it with a value for a. So they put 2 in for a, and they get 5 times 2 plus 15 all over 10. They get 5 halves. Well, if I take my simplified expression, I should get exactly the same value, or I've made a mistake. And in this case they do. You just get 2 plus 3 all over 2. And you think about that. If I needed to evaluate this expression, I would rather evaluate this over here, right? It's pretty simple. Gets rid of some multiplication. Now, we could try that with different values. And, let's say if I simplified this incorrectly and said, and this is a real common error, is to rewrite this as a over 15, as you think, well, when I take this common factor of 5 out, and then forget to take the common factor away from the 15 too, and leave that. So this is a incorrectly simplified expression. Well, we can catch that. If I use 2 here, I get 5 halves. In this one, if I put 2 in, I end up with 17 halves, so there's a problem. So there are some ways to check your work on this stuff. Now we're going to get a little more complex. It's not really more complicated, and I can't emphasize that enough. I mean, we're really just trying to create fractions equal to 1. So I factored, and we kind of start with some easier factoring. And there's that strategy that we're going to go through, and I'll try to bring it up as we run into these examples that use that. And so in this case, like example 4, I need to factor the numerator, and then I'm going to factor the denominator. Well, what do you look for first? I look for common factors, which there are here, 6x and 12, and 7x and negative 14, if I want to say it in terms, say that this is really a negative 14 term, is that I factor these, I end up with 6 times the quantity x minus 2 up on top, and here I get 7 times the quantity x minus 2. Now that they're factors, things that are multiplied together, we can break this up into different fractions. So I get 6/7 times x minus 2 over x minus 2. Well, x minus 2 over x minus 2 is the same denominator and numerator. That's equal to 1. So by removing the factor of 1, which is, I don't know if I like that term, but basically I do the multiplication by 1, and I get 6/7. So this expression simplified, I get 6/7. Now that way we were talking about simplifying this might be pretty hard. You'd think, well, I can't just put 2 in there, but put 2 in there. If you put 2 in there and try to check that, guess what? You're going to end up, after you simplify the fraction, you'll get 6/7. Okay, so in this case here, we want to do this. Now they jump, basically this can kind of throw you in factoring because the book knows what they're going to get for ones as they're writing this out. So I would look at prime factoring this thing, right? Really what I have is 6t is common here, so I'd end up with 6t times 3t plus 1. And then that's where I talk about prime factoring. Because a lot of times this is missed. Is you go, well, 6t is really 2 times 3 times t, is the way I would write this. And then I know everything is prime. Every factor is prime. I know I can't factor anymore. That's a good way to make sure you've factored completely. Well, this denominator, 6t squared plus 15t, the common factor between these two, again, because you always look for that first, is 3t. Now 3t is just 3 times t. Those are both factor, and then this, or prime, excuse me, factors. And 2t plus 5 is a binomial. I can't factor that anymore. So that's prime. So then I would recognize, hey, I got a 3 and a t that's common between these numerator and denominators that are factors. I can rewrite this as 3t over t. I get 1 times this expression. Now I would, a lot of times I see students do this. I would leave it this way, but you could write this as 6t plus 2 all over 2t plus 5. That works too. But you're just taking an extra step that gives you the possibility of making some kind of math here. So I'd leave it just this way. Don't take additional steps if you don't need to. This example C, we have a trinomial over a binomial. So I look to factor this. First thing, what do? Is you try to find common factors on this numerator. Well, there's an x and an x, but no x here. No common factors. Well, then a trinomial, then I look for perfect square trinomial. This is something squared. This is not something squared, so I don't have a perfect trinomial squared. So then I use the grouping or anti-FOIL, which is looking for factors of 2 that will add up to 3, which is pretty obvious, okay? So we rewrite this trinomial as x plus 1 times quantity x plus 2. Now in the denominator I look for common factors first. There are none in this case. And then I have a binomial. When I have a binomial, there's only 2 things we can factor. It's difference of squares, where it's first term squared minus something the second term squared. Or we also have sum of cubes and difference of cubes, that we have some pattern factoring that we can do. Well, this happens to be difference of squares. We always look for difference of squares first because that's simpler. It's an easier thing to factor. You'll get a lot better results if you do that. So they factor these 2 things. These numerator and denominator, they get x plus 1 times quantity x plus 2 on the numerator, and the denominator here is difference of squares of x plus 1 binomial times a binomial x minus 1. Well, here are our common factors. I can create a 1 out of that. So I arrange that in a way that it's going to be equal to 1. 1 times this thing, and I end up with this new expression of x plus 2 over x minus 1. Okay. Now they kind of show a shortcut here called canceling and simplifying, which might cue up some of the things we've done with fractions before. I think it will serve you much better to get really solid with this idea. Now, it doesn't mean you have to write this out all the time. That's kind of what this was meant to do, but it kind of gets misused as a shortcut, and we forget what's really going on here with fractions equal to 1. Okay? We talk about canceling, or you keep reducing till you can't reduce anymore. The reality of a simplified expression, rational expression, is that they're relatively prime, is one way to say that. I don't think it's referred to in the book that way. But the greatest common factor between the numerator here, x plus 2, and the denominator, x minus 1, is 1. Okay? And then we know that it's in simplest form. A couple cautions. One thing I do like about this textbook, I've probably said this several times, is they really do. I see this when I'm correcting papers and going through work. I see this all the time. Is you forget about order of operations, really. I can't break up an addition and just start cross-canceling or doing those kind of things. It's probably one of the bad habits that comes from just thinking about canceling things out. I can't write this as x over x plus 7 over 3, which would be 7/3 no matter what I put in there. Those kinds of things. And a good way to do this, again, when I talked about that, put a number in there. If you think you can simplify this x plus 7 over x plus 3 to be 7/3, like they're kind of showing here with the crosses, well, try it. Put 1 in there for x. 1 plus 7 is over 1 plus 3. You get 8 over 4, which is 2. That didn't work, did it? It isn't equal to 7/3 according to your simplification if you made this error, right? Same thing here. Try that. If you're not sure, or even if you are sure, I would check these things to go this way, where they're just basically showing us a few ways that you see incorrect simplifications. And example 5 here is probably the more complex. Really, when you have two trinomials, there's a lot more things that can happen. Again, we have difference of squares, we have sums and differences of cubes. We have 4-term things that we can factor through grouping, those kinds of things that are going to come up from that we've gone through in chapter 5. But let's go through this again. For example 5. And this is probably a little harder when you have a coefficient in front of your first term. And we still go through the strategy, so I'm going to look just at the numerator now. 3x squared minus 2x minus 1. I look for common factors. Well, this is 1. The only common factor with 1 is 1, so I'm done. There isn't any common factors here. Then I look for factors of 3x squared and factors of 1 that I can get a combination of getting this middle term right. So we do this, and you end up with this being factored to be 3x plus 1, the binomial times this binomial of x minus 1. Then we factor the denominator, we get x minus 2 times the quantity x minus 1. These are common. In other words, I can write this as x minus 1 over x minus 1, which is equal to 1. I'm happy they still do this in the red on the right. You'll kind of notice they do less steps as we move on, and they are going to give us less information because, when you get further into this course, you're going to be expected to know the prior things that we've covered more. So I think I'll stop there, and I'll do this last part, factors that are opposites, which there seems to be a lot of problems with. or errors that occur around negatives, really. So I'll stop there and we'll finish the chapter in the next, or this section in the next